Like so Fn is Cn times the indicator function of what? Lambda naught minus 1 over n and lambda naught plus 1 over n. Agreed? This is what that is. Now what does this mean? This means that Fn of t is a Cn if t is in this interval, okay, lambda naught minus 1 over n to lambda naught plus 1 over n, okay, plus 1 over n, okay, or I can rewrite this, that this is same as that t minus lambda naught is less than or equal to 1 over n, okay. So what is this Cn? I am not choosing it at the moment. So I can choose it afterwards. So in such a way that whatever I want, I will get it. And it's equal to 0. Okay. When t minus lambda naught is bigger than or equal to, bigger than, strictly bigger than 1. Okay. So this is what my function is. Now I want to what? I want to be. I want this guy or the norm of this guy to be 1 actually. Yes, sir. So let's compute the norm of Fn t square. So we're going to get 0 to 1 and Fn of t square and t. Okay. Now I can do what? I can break this integral into two parts. Okay. So I can say that this integral can be written in two ways. So one way is that when the distance of t minus lambda naught is less than or equal to 1, okay, square of t, plus when t minus lambda naught is strictly bigger than 1 over n. So would this cover whole 0 to 1? Think about it.
Yes.
Yes, sir. So it could cover it.
Yes.
Okay?
Yes, sir.
So what would be the Fn square in this interval?
Cn
square. And what would be the meaning of this if I write it explicitly? The meaning of this would be so this guy, this interval actually. So lambda naught minus 1 over n, lambda naught plus 1 over n. And the second thing is going to be 0 dt, whatever it is. I would say that this would be 0 essentially. Okay. So if I simplify this, what are you going to get? Okay. So what would be Cn square? So it's like a 2 times of Cn square over n actually. Okay. I want to turn this guy into 1. Tell me what should I do? So what if I choose a Cn to be scale of n over t?
Yes, sir.
Okay. So if I choose this Cn, okay, so in each interval, so I'm gonna get what as an outcome? Are you getting the point?
Yes, sir.
So what would be the next thing? So we achieved the first condition that the norm of Fn is 1 actually. Okay, so for each n I will have a Cn which will turn the norm of Fn into 1 actually. What would be the next thing? The next thing would be to do this approximation actually, that okay, the eigenvalues, so it's like this equation is not true in general, but it's true for the sequence actually. So in other words, it's true in some approximate sense. Okay. So what would be this? So this is going to be that I need to compute AFN minus lambda naught Fn square n2. So the definition tells me that I need to compute the integral of AFN minus lambda naught Fn and operated on the T and dt. And this would be an obviously it's a square. So this would be 0 to 1 and it's going to be Tfn minus lambda naught Fn square and dt. Okay? And what I'm going to get as 0 to 1 T minus lambda naught square and Fn square and dt. Okay? Now I have two options for T minus lambda naught. So one option is that when T minus, in other words, I can break this integral into two parts. So one part when T minus lambda naught is less than or equal to 1 over n, and the other part is when T minus lambda naught is bigger than or equal to 1. In that part, when T minus lambda naught is bigger than 1 over n, Fn is 0. Okay, so I don't need to care about that. So the only thing that I have to care about is the case when T minus lambda naught is less than or equal to 1. So in other words, I would say that I can estimate this by 0 to 1 Fn of T square, okay, over 1 over n square actually. Okay? Is it making sense? And less than or equal to, what is this guy? So this guy is nothing.
No.
Okay? So this guy is nothing, but this is 1 actually. Because that's what we did. So we chosen Cn in such a way that the norm of, because this would be what? This would be the 2 norm square of Fn. And this is what? This is 1 actually. This is 1. So you're going to get 1 over n square, and that goes to 0 as n goes to infinity. And this is what the end of the story is. So what does this shows is that this multiplication operator doesn't have eigenvalues, but this multiplication operator has lots of approximate eigenvalues in the interval 0 to 1. Okay? Making sense? Like a result, write a result, not prove it. Okay? If you wish, you can see the proof from book. I'm not going to do it. Pretty simple proof. It's not our main intention to do today.
Sir, जो हमें eigenvalues लिए वो with respect to दो vectors जो हमें sequence बनाए थे.
Yes.
तो यही क्यों नहीं? कैसे पता चला कि यही लेनी है? हमने जो function fn define किया, sequence भी define किया, तो हमें कैसे पता चला कि इसी से ही?
That's what the clever thing is, that you have to do construction. Okay. It's not an easy task. This comes with experience. Okay. There is no shortcut. Once you will learn more and more, you will learn basically these tricks. So the essential, what do you call the trick is that, okay, what I have been given and what I want. So let's make choices in such a clever way that you get what you want. No shortcut. Like a lemma, which says essentially is compact. Okay? Imagine we have a Banach space and a compact operator. Then every approximate eigenvalue is eigenvalue. That's it. That's what it says. if you have a compact operator and you can find some approximate eigenvalue, then all those eigenvalues are basically eigenvalues. So every approximate eigenvalue is eigenvalue. You can just prove that. Okay. Lambda is 0. Approximate eigenvalue of A, then lambda is eigenvalue. Okay. So for compact operators, you have certainly something pretty interesting, that if an operator is compact, then every approximate eigenvalue is eigenvalue. As I said, this thing is much easier to achieve actually. Okay, so what you just need is a sequence and a number for which this is true, and hence, you can claim that that value is approximate eigenvalue. But if your operator is compact, obviously on Banach space, then every approximate eigenvalue is eigenvalue. Okay? I'm not doing its proof, so just mentioning this result. So it's a pretty interesting result. What would be its contrapositive? Think about its contrapositive. So you want to show that an operator is not compact. Just show that this operator has an approximate eigenvalue which is not eigenvalue. Okay? So if an operator has an approximate eigenvalue which is not eigenvalue, okay, then A can't be compact. So, pretty interesting thing actually. So always think about contrapositives. Contrapositives give you pretty interesting information basically. So I would like to move to our key topic today, which is what do you call the self-adjoint operators. Okay. Okay. So what is key definition? The key definition is that an operator A on Hilbert space H on Hilbert space H is self-adjoint if what happens? So A is same as A star. That is, AFG is same as FAG. Okay? For all F and G from H. So if this is true, your operator is a self-adjoint operator. Okay? What are some examples? Of self-adjoint operators? Number one. So if you remember, in the first bit I gave an exercise, or maybe what do you call a bonus problem, and if you remember, in which for the projection operator you are set to prove something similar. Okay? And some of you did it correctly. So you remember that? It's like EFG is same as FPG. So the projection operators are self-adjoint. So one of the key example is that each orthogonal projection Okay? Projection is self-adjoint. So orthogonal projections are self-adjoint. So not going to do it. You did it already in exam. Okay? Yesterday we did an example. We said that if A is Hilbert Schmidt, okay, A is Hilbert Schmidt operator, okay, with kernel K, with kernel K, then A star is what? A star is also an Hilbert Schmidt operator,
Kernel K.
Kernel K.
but Schmidt with kernel K star. But what was K star?
K bar.
So K star was K bar. Okay. Now, if I have a kernel, so it's like I have a Hilbert Schmidt operator for which K bar is equal to K.
Only for us.
Okay. So if the K bar is equal to K, then Hilbert Schmidt operator is
Self-adjoint.
self-adjoint. Now, if, and this if is big if, it's not true in general. So if K bar is K, then operator A is self-adjoint. So it's like, okay. So one of the key things, so think about it. One of the key thing that we can have is that if you have a Hilbert Schmidt operator with a real kernel actually, with a real kernel, some exponential or something, okay, because we know that if the kernel is real, its conjugate is going to be itself, so it must be self-adjoint. Okay, not like the Fourier transform, because in Fourier transform the kernel is exponential, but exponential with the complex number, and it's not necessary that for that transform the kernel is, the conjugate of the kernel is same as the kernel. Okay,
Laplace is positive real kernel.
but it's not Hilbert Schmidt. It's not Hilbert Schmidt. It's not Hilbert Schmidt. Did it make sense? So we did two examples. So let's move about some of the key properties of self-adjoint operator, and where we are going to end our story. Talk about some of the properties of self-adjoint operator. I'll prove some, I'll just discuss some without proof. Okay? But I mean, the proof that I'm not doing, they are readable proof. You can pick book and you can read it. Okay? And I highly encourage you to finish this book actually. In other words, the things that we haven't done in the class, and obviously we can't cover everything in the class. So the stuff that we haven't covered, just read through it actually. And it's going to give you what you call the more richness in the course, okay? Or maybe of the function analysis. So here's a little theorem that I would like to do. Okay? So let A from H into H, where H is a Hilbert space, be a self-adjoint operator. Write this, that A be a bounded self-adjoint operators. Operator on Hilbert space H. Hilbert space H. Then it has this pretty interesting property. Then this inner product AFF is always a real number. Okay, this inner product of AF and F is always a real number. It can't be a complex number. It's going to be always a real number, and if you compute the norm of A, then how you can compute it, just take the supremum of all these inner products with on F, or with F, but those F's for which the norm is known. Okay? For which the norm is known. Obviously F must be from H. So in other words, if A is bounded and self-adjoint, this inner product, okay, this duality must be in always a real number, and just taking the supremum of such inner products for those F, not in general, for those F for which the norm is 1, okay, you're going to get the norm of A. Okay? And this quantity, okay, is sometimes called numerical radius. The numerical radius of it. Numerical radius of it. Okay. Let's prove that why this must be real. Why this must be radius? Think about it. So, okay, when a complex number is purely real, what condition must be satisfied? Huh? Okay, but when imaginary part is 0, if I say you that, okay, tell me what condition, so if Z is a complex number, what condition must be satisfied so that it must be if the conjugate is itself. Okay, so compute the conjugate itself. So I'm saying that what is AFF actually? So I want to show this real. So if I show that okay, this is equal to its conjugate, I'm done. Okay. So it's equal to what? Give me. So A is self-adjoint. So it must be same as F AF. Okay. So can I bring this quantity here? How can I bring it?
By a bar.
Well, just put the. Okay. Now I'm done. Okay. So what does this show? That the conjugate of this guy is equal to itself. So this must be real. Okay. Nothing too much difficult. What is the next thing to show? The next thing is to show is basically this guy. Okay, that if you compute the norm of A, so we have a definition for the norm of A, okay, which is different from this. So if I treat this as a set, and I compute its supremum, and it turns out to be in agreement with, the norm of A, then, I'm done. So this is what that I would like to do. So what I would like to show is that, okay, let's begin with Cauchy-Schwarz by Cauchy-Schwarz. What will be the absolute of AF and Fn?
Bounded with norm of A and F.
Huh?
Norm of A and norm of
So it must be less than or equal to norm of F times, norm of AF, norm of AF times norm of F. Agree?
Yes.
Right?
Cauchy-Schwarz.
So norm of F is 1. Why?
Yes, sir.
We have this assumption. But this is less than or equal to
Norm of A.
norm of A times
Again,
norm of
F1.
F, which is again 1, which is equal to norm of A. Okay? So somehow, for all such number, norm of A is an upper bound. So if it is an upper bound, if you take the supremum of all such values, that would be the least upper bound for such values. And the least upper bound is always smaller than or equal to upper bound. So I can say that if you take the supremum of, like such AF and F, okay, so it's always be less than or equal to norm of A. So one side is done. So you just need to show the other side, okay? Alright. To begin with the reverse part of inequality, I have to do a bit more. What? I have to do a bit more clever things. It's not as straightforward as it should be. Okay? I need to do some calculations to show the reverse inequality. Okay? So let's begin with this actually. So A operated onto U plus V, where U plus V are just like for U V in H, consider this guy. A operated onto U plus V and U plus V. Okay? And subtract what? Subtract A times of U minus V and U minus V. Okay? And I am saying that, okay, do all simplifications, cancellations, and so on and so forth. What you're going to remain with, you're going to remain with 2 times of AU, okay, AUV, and plus 2 times of AVU. Okay? This is what I'm going to get. So A is linear, and I can do all these calculations, and it turns out that no, it is actually, obviously. You need linearity. Explicitly there. It's linear. It's not explicitly mentioned, but it's like self-adjoint operator must be an operator. Must be linear operator. So linearity is everywhere. So we are not going to consider, we haven't considered throughout the course anything too much non-linear. Okay? So linearity is always there. And this would be same as what? So 4 times of real part of AUV, AU. Do you agree with this? Huh? So I have used so-called the polarization identity and symmetry. Okay? So maybe a good thing to verify actually. Okay, so polarization identity, and it gives you this. So now I would like to compute what? I would like to compute what? So what would be the relationship between R, AU, V absolute of a real part of AUB. What will be the relationship between both? Must be less than or equal to.
Yes,
The
sir.
number
The
is
earlier part
always
can be
less than or
negative.
equal to its absolute.
Yes, sir.
Okay. If I
Sure.
take